So good noon to everyone. Professor Sarbajit Banerjee is the Davidson Chair Professor of Chemistry, Professor of Material Science and Engineering, and Chancellor EDGES Fellow at Texas A&M University. I invite Professor Sarbajit Banerjee to deliver his keynote lecture on designing catalysts for water splitting based on electronic structure considerations, which is a very high topic in the current scenario. Professor Sarbajit Banerjee, please.
Thank you so much, Toki, for a very generous, long introduction. It is a real privilege to be able to speak to this audience today. It's a very diverse audience. And so I have a mix of materials. I'm going to start with some introductory material, and then depending on how much time there is, we'll get into some details and of how we think about this problem. Okay, so let me start by acknowledging the people. So most of the work I'm going to talk about was funded by the National Science Foundation and Vanitech, and it was initiated by a grant from the Research Corporation for Science Advancement. And this is my group. Of course, we haven't been able to take a group picture in a while, but I will call out some specific contributions as we go along. Most of this work is done with the group of Dave Watson at the University of Buffalo and Professor Lewis Piper at SUNY Binghamton, and several other groups that I'll kind of mention as we go by. So just let me start with some general thoughts about energy. This is one of the themes of this conference, of this webinar, and we all rely on energy. Our generation uses much more energy than previous generations have ever had access to. And if you think about the electric grid, right, the grid, the power that comes into our homes is in many ways a method for giving us freedom, right? It gives us freedom from darkness. It gives us freedom from cold, from heat. It gives us freedom from boredom. It gives us the freedom to communicate. So in a sense, energy is a tool of freedom, right? So without energy, we cannot really have or enjoy our freedoms, right? So the energy really makes it possible for me to sit here and communicate from thousands of miles away, right? But energy is not free. It comes at a cost. So in 2018, 1,763 million metric tons of CO2 were produced from electricity generation, right? And in 2018, 83% of all electricity generation in the US was from non-renewable sources, right? So this situation is fast changing, but while on the one hand, this is an interesting sort of balance to think about as scientists, right? On the one hand, energy is a tool of freedom. On the other hand, energy is messing up our climate, right? So our demand for energy is messing up the climate. So we need some we need some solutions here. And current global policies related to economic consumption, related to the growth of populations, related to our use of more and more energy could lead us to up to 4 degrees C of global warming by 2100. So this is a huge challenge that our generation, that the next few generations have to solve. So there's a lot of urgency to it, right? So it never has it been more important to be a scientist, right? So I think Jamia has this incredible tradition of training scientists, not just doing great research, but also training researchers who go and establish their own labs and teach science across every corner of India and across the world. And I think there's more of a need for that now than ever before, right? So we have to have a lot of emphasis on science if we're going to solve these issues, right? So less money on things like defense, more money on things like that will solve these crises, right? These massive crises that we face. And so part of the challenge, again, the Paris Climate Agreement wants us to, countries are committed to a 1.5 degrees. We're already at a 1 degree C warming of global temperatures. We've got a lot of things going on that is going to be impossible to turn the clock back on. So if we're going to limit global warming to 1.5 degrees, there's a lot of urgent technological innovation that is needed, right? So, okay, we have Dr. Sarma gave a beautiful talk thinking about solar energy and thinking about hybrid perovskites, and he's going to actually, he saved me a lot of introductory slides there. So there is a lot of excitement about solar taking off, wind taking off, and coal is clearly declining. So there is, you know, we are kind of in this mode of the energy transition. We're moving. This is sort of a once in a lifetime, once in a few hundred years event where we are moving from a paradigm which is emphasize fossil fuels to clean energy, right? So hydropower, wind, and solar, right? And by 2050, renewables will be about 49% of all energy electricity generation, and hopefully we can get there sooner, but that's going to require, you know, policy interventions and a much stronger effort by the government. So solar is great and wind is great, but it comes with challenges. So with wind energy, you can see here there's some major issues. More than 54,000 wind turbines are installed in the U.S. We've had this massive increase from 2007 to 2017, but wind doesn't always work, right? When the wind is not blowing, it doesn't do very much good for us. Again, solar energy, the average price of solar panels has dropped nearly 50%, and the existing solar panels in the US have enough capacity to power millions of homes, and this number is constantly increasing. But again, you don't have solar at night, you don't have solar on cloudy days. Sometimes you've got multiple days, weeks of rain and clouds where the solar is not very effective, right? So what do we do here, right? So thinking about how our grid is going to change and designing for you know, accommodating these green energy sources will mean that we're going to have to build in mechanisms for energy storage, right? So if you think about this is a nice plot from the U.S. Energy Information Administration. You know, something like nuclear is on all the time. Natural gas and coal are quite reliable. Wind and solar much less so, right? So only 25% of the time, approximately, solar is working. About a third of the time, approximately, wind is working. This really requires a whole change in paradigm for electric grids, which are typically our electric grids are made so that whenever there's demand, we produce more power and we fulfill it, right? And we're not really used to saving power and then using it as required. So this is going to be a big change for us, and this is going to require a considerable complexity, right? And so an out of balance grid. So this is generally at any moment, power plants generate just about the same amount of electricity that customers demand, right? But if you've got solar and wind coming on board in a big way, this is going to have to change. We're going to have to really rely on storing energy, not just generating energy, right? And energy storage is a very, very big problem. So you know, we're going to talk about this, spend some time thinking about this fundamentally, right? So energy storage is important because it decouples electricity generation from the load or the electricity user. And so it makes it easier to regulate supply and demand, right? So if you've got a whole bunch of energy stored, you perhaps don't need as much capacity. You can rely on you know, creating a lot of energy in the downtime and using it when there's peak load, right? So this makes it easier to regulate supply and demand. And it allows also, this is a very important notion, the distributed energy storage, right? So you can have local grids, microgrids, and you can therefore improve energy security quite a bit. So that means that, you know, the more interconnected grids are, a lot of times the more risk there is of entire grids collapsing, right? And we've seen that happen across the world several times. Multiple options for storage. I'm talking about two chemical options. There's lots of mechanical options like compressed air or pumped hydro, which you can also use. But you know, in the context of materials, we'll think about two batteries and hydrogen. I'm going to spend most of today, right, given the theme of the webinar, focusing on hydrogen, and then I have two lectures and the rest of the week thinking about electrochemical energy storage and batteries. Okay, so and again, energy storage, the need for energy storage is widespread. we need energy storage on the scale of the entire grid. And you see some, windmills here, and the windmills have to be connected to energy storage here. Also, every type of electromobility, all the way from electric cars to electric vehicles, to buses, to small portable, small scooters, and all the way to electric airplanes, right? So there's a need for energy storage for all sorts of mobility, so that we can get rid of the liquid fuels that are contribute so much to CO2 emissions and SOx emissions and NOx emissions, and stop burning liquid fuels that are at the origin of climate change, right? So for energy storage, we have to worry about a lot of different issues. How much power can you get? How much energy? What sort of safety? Sometimes you might think about portability if it's a mobility application. Understanding how to retain capacity over a long period of time, because generally, you get pretty upset when your cell phone battery starts to die after about a year. When it comes to the whole grid or a car, you can't dispose it or upgrade it in a year, so you really need to have much more capacity. And there's a whole lot of options out there, And the point of this, of showing this, I want to emphasize: there's no winners or losers. It's a matter of each of these are going to have a role, and each of these are going to play a role in some form or the other. So, for instance, here, vanadium redox flow batteries are going to play a big role for long-term energy storage for multiple days. There's huge projects coming online in China, potentially across the EU. There's, of course, lithium-ion battery is the dominant paradigm for electromobility and consumer electronics. And then you've got lead-acid batteries in certain applications. And so this is really a huge sort of set of opportunities. And I think just thinking about it for young people, electrochemical energy storage, electrochemistry, the interface of electrochemistry and materials, there's going to be so many jobs here, because we're going to be so reliant as this energy transition takes off. We're going to be seeding so many industries and a whole new look at manufacturing across the world, right? I'm going to focus here today, like I said, mostly on hydrogen, and I do have a couple of lectures in this coming week focused on batteries. Okay, so hydrogen, as we use it today in the world, most of the hydrogen that we use comes from methane steam reformation, which is not a clean source of hydrogen. Okay, so if you're in the Middle East and you're using natural gas and you're generating hydrogen from there, it makes sense. But to do methane steam reformation just to get hydrogen is a pretty nasty and sort of carbon intensive way of generating hydrogen. So ideally, really, we'd like to move towards a whole different paradigm of getting hydrogen, clean hydrogen from water splitting, right? And why is hydrogen? Why am I equating hydrogen to batteries? Because in a sense, it's just a chemical fuel, right? You can fill it in a tank and you can burn hydrogen, and this is sort of elementary chemistry. Hydrogen, when it burns in oxygen, gives you water, and so it's essentially unlike the fossil fuels. You can get energy out of this without generating carbon dioxide, right? And if you can generate hydrogen from water, and if you can do it using solar energy, which is a free and non-polluting source and a renewable source, that would be ideal, because that would really make a difference, because we could be essentially harvesting the solar energy, storing it in the form of hydrogen, right? So how do you do this? Well, the challenge with doing electrolysis, right? You can just take water and you can run a current through it and you can generate hydrogen and oxygen. But the overpotentials that are required essentially means that it's a very inefficient way of generating a hydrogen, right? So then that brings us to our next question. Can you have some catalysts that can reduce the overpotential? And then can you directly harness sunlight to do it, right? Without necessarily going through this converting solar energy to electric energy and then electric energy to chemical energy. Can you directly go from solar to chemical energy, right? So you can excite. That's what was shown here in a semiconductor. And Dr. Sarma set the stage for me by explaining about what a semiconductor is, so I don't have to get into too much details here. So you can excite an electron up into a conduction band, right? So the electron can be used to reduce a proton to hydrogen, and the hole that's here can be transported to oxidize water to oxygen and protons. And those protons then just have to come from this side to the other side, right? And the excited state electron and the excited state hole are generally more strongly reducing and more strongly oxidizing than your regular electrons and holes. And that really gives you the opportunity to do more chemistry that is not spontaneous in the ground state, right? And I'm showing a relatively simple scheme here. There's a lot of interest in all kinds of solar fuels, even beyond hydrogen and oxygen, but we'll mostly focus today on this, right? If you compare this to the solar cell example Dr. Sarma showed, where the only difference in the solar cell, you do the same thing. You take a semiconductor, you excite it, but then you flow that electron across an external load, and the current times the voltage gives you power, right? And that's the only difference from a chemical energy conversion system. So what is the world's best photocatalyst before we came along? There already exist photocatalysts that are doing this every day, every someplace in the world, that are taking protons and reducing it, and that are taking water and oxidizing it, releasing oxygen. This happens all the time, right? So who does it? Well, leaves do it, right? Leaves. So the whole concept of photosynthesis really involves splitting water, right? And generating, taking NADP plus and taking that hydrogen and making it NADPH, and releasing oxygen, right? So this is the role of plants and afforestation and reducing and capturing, and generating oxygen, right? So the challenge we have is a difficult one, is to mimic photosynthesis, which has evolved over the course of millions of years to mimic it in artificial systems. But we can't just mimic it, we have to do it more efficiently, because plants are great, but they're slow, right? And even the fastest growing species that, for instance, algae, are still slow compared to what is achievable in a catalytic system, right? So our targeted reaction is water splitting. The challenge is that it's a multi-electron reaction. We need to basically move 4 electrons and 4 protons, right? And so if you think about this is not trivial. You've got to get electrons and holes to go in the same place. And this is a theme that I think came across in Dr. Sarma's talk as well. Much of modern material science has to do with understanding how to control not just static materials, but dynamic materials, right? Materials that will flow, charge, mass, energy across multiple decades of length scales, okay? All the way from atoms to systems. And one example Dr. Sarma talked about very nicely, he talked about the silicon age, and you're using mobile phones and laptops that are made of silicon and many other components, right? And it's so precisely engineered across about 10 length scales, right? So from all the way from nanometers, the 10 nanometer transistors he talked about, all the way to these macroscopic objects that we're dealing with, right? So there's a huge sort of range of properties, right? And then you also have to have processes happen from femtoseconds to seconds, right? So how do you design these materials to basically function as an artificial leaf? And this is a little joke. Organic chemists sometimes use this periodic table. But how do you do this? You can search crystallographic databases. You can modify known materials. You can essentially combine materials together in heterostructures. We talked about composite materials. Dr. Sarma answered the question about this, and it was a great question in the chat. So you can combine materials together and get material where 1 + 1 is more than 2, right? That's the whole purpose of this. Or you can make altogether new compounds. So it's just important to remember that when we think about the whole world of materials chemistry, if I just stand at a periodic table and if I throw 3 darts at it, if I just pick 3 random elements out of random, only 5% chance that you will land on a material that is known. There's 95% chance you will land on something that is not known, right? If I pick 4 elements, there's a 1% chance, less than 1% chance of landing on a unknown compound. So 99% chance you will land on a compound that is completely unknown, right? So, when we think about all these important challenges that need to be tackled, it's also important to understand that we haven't explored much of this world, right? This whole periodic table stands unexplored, and there's so much chemistry that needs to be done, right? And then I also want to think about this for a second. We think about something like graphite, for instance, something you're familiar with, right? Is the thermodynamically stable form of carbon. That means that it is the lowest energy minimum in a free energy landscape, right? But there exist other forms of carbon that are not the lowest energy minimum, that are nevertheless quite stable and have very interesting properties. One of them, of course, being diamond, right? So diamond under pressure many years ago, and then slowly released, diamond got formed, and it's a metastable allotrope of carbon. Carbon nanotubes that Dr. Sarma talked about, or buckyballs, are other examples of reasonably stable but metastable forms of carbon. So for every set of atomic compositions, you have many possible structures, right? And so if you consider what I showed in the last slide, this vast realm of possibilities in terms of different elements, and then all the vast realm of possible atomic configurations, we're dealing with this huge space that we haven't properly sampled, right? So there's, in a sense, like the ancient explorers discovering new lands, there's this vast expanse of the periodic table that remains uncharted, right? That holds great mysteries, that holds great promise for solving some of these biggest challenges we have in our world, that hopefully generations of students, including from Jamia across the world, will work on, being explorers of this periodic table, explorers of new chemistry, new physics, right? So, okay, let's get down to this. So we've got to catalyze this water splitting reaction. This is the fundamental work by Honda and Fujishima, where they took TiO2 and they linked it with platinum, and they were able to get this reaction to happen. A lot of conventional systems will invoke 2 semiconductors to separate electrons and holes. I'm going to focus most of the rest of my talk thinking about these nano-engineered heterojunctions and really thinking about how do you design an artificial leaf, right? And so there's a lot of complexity involved, but I'm going to try to take you through how we think about this system. And from the perspective of the question that was asked in the previous session about a composite, like here is an example where we are trying to build together a heterostructure where each of these components play a different role, and together they have basically set in motion a cascade of processes that result in this desired production of solar fuels, right? And again, what we're trying to do is mimic a leaf where you have a division of labor, right? You don't have one material in a leaf that does everything. You have this divide and conquer method of harvesting the solar spectrum. So on the one hand, you've got absorbed light, we've got to absorb the light, we've got to harvest the solar spectrum as effectively as possible to generate electrons and holes. We've got to take, using a large traditional wide bandgap metal oxide semiconductor like TiO2 squanders a lot of available energy, and TiO2 does not have very good overlap with the solar spectrum, mostly just harvesting UV light. So we're going to have to solve a whole bunch of these applications, right? So we're basically we're trying to absorb light effectively. We're trying to separate charges, and then we're going to try to get these redox reactions to happen, the reduction reaction and the oxidation reaction, right? And so this is our goal. What we have in mind is a light harvester that is hooked up with um, a dark catalyst that does water oxidation by blowing a hole to it, and then a catalyst that does hydrogen evolution, right? So these essentially these little structures start to mimic artificial photosynthesis. So let me sort of dive down a little bit deeper into this. Okay, so on the one hand, the first thing we need to do for photocatalysis, you need to harvest light. Okay, that's the most important thing. So let's focus here on Dr. Sarma also gave a great introduction to quantum dots, including chalcogenides, more conventional quantum dots, as well as the new amazing perovskite halide quantum dots, right? And the point is, what is so great about quantum dots? Well, they've got very large oscillator strengths. That means they interact very strongly with light, very strongly light absorbing. They have size-dependent optical properties, like you saw. You saw some beautiful pictures here. I'm not going to dwell on that, right? So compared to dyes, they can have sort of multiple orders of magnitude stronger interaction and absorption. You can get multi-exciton generation. So for one photon of light, you can generate multiple electron hole pairs. You've got rich surface chemistry that you can use to tether it to different species, like we saw what TiO2, right? So this is the goal. And I'm going to spend not too much time thinking about this. We're going to use this as a primary light absorber, but there is a major challenge to quantum dots before I move on that I wanted to talk about. So quantum dots have been great in solar cells. Both chalcogenide quantum dots, as well as especially perovskite halide quantum dots, there's a major problem that we have to deal with if we want to use them in conventional photocatalysis, and that's the fact that they degrade in the water, right? So if you're going to use these to generate hydrogen and oxygen, they tend to be extremely unstable. And for quantum dots, the reason they're unstable is because they undergo photocorrosion, right? So they absorb light and then they photocorrode, and then they fall apart. So one of the biggest challenges that I'll tell you about solving is how do you prevent photocorrosion of the quantum dots, okay? But before I get there, I just want to spend a little bit of time also thinking about the future of chemistry, right? You know, the future of synthetic material science, future of chemistry. I think we're all used to, if you ask, if you think about, if I tell you to draw a chemist, most of you will draw a chemist, wearing a lab coat and perhaps with beakers and such in hand. I think there's a really big revolution coming here as well, which comes from automation, laboratory automation, and machine learning. The idea, I think 10 years from now, certainly 15 years from now, but in our lifetimes, I don't think PhD students and research scholars will be doing synthetic nanomaterials chemistry. I think what we're going to have is be moving to a bunch of robots that will be preparing these. And I think that'll be a great thing, because it'll mean that reactions are not dependent on who's doing it, on what sort of day it is. Things are going to be a lot more precise, and of course much more safe for people to handle. So the world we're talking about, of course, the robots will need to be powered by machine learning. So this is the work of Jun-Sung Cho and Eric Bram, who have we've taken the perovskite halide quantum dot system, and we've studied the synthesis of it. There's a lot that goes in, right? Precursor, solvent, ligand, temperature, concentration, mixing conditions, heat treatment, and how do we build a model such that you can have a robot make these and build with machine learning predictions that will allow us to very precisely control the dimensions of a quantum dot. And so this is an example of a machine learning model that Eric and Jun-Sung have made, and we can look at different. We took 74 different experiments with different chain lengths, temperature, concentration, chain length of the amine, and we can measure the size response using photoluminescence. And by doing so, right, we can generate a classifier, and then we can generate a regressor. And so here's the idea. essentially our goal one was to accurately predict conditions that lead to quantum confinement. So we took these 70 odd experiments, and we were able to understand based on a support vector machine methodology. So what are the conditions that will get us a quantum dot, as well as as compared to conditions where you get bulk samples, right? And this is the importance when you're handling multidimensional data for really moving beyond linear regression into these models like support vector machine that can give you very well separated data, right? And then this allows us with relatively little experiments to build a detailed model of how the unit cell thickness of the quantum dots, the perovskite halide quantum dots, vary as a function of multiple parameters like temperature, concentration, diffusion coefficient, and you've got vast dimensions of space you can sample in a chemical synthesis, and can you map these models and very accurately predict how to get to a 2-layer or 3-layer or 4-layer perovskite quantum dot, by having a very accurate model. And in fact, the model is also great for understanding mechanism, because when you actually start looking at regions of the space, you can say, well, okay, I understand why this is 1 layer versus this is 5 layer, and has to do with the enthalpy and entropy of ligand shell passivation around these methods. So the moral of the story here, just a little interlude, is that when we do energy science, and I told you about this vast multitude of these species that we are going to have of energetic space, of compositional space, as well as structural space we're going to have to explore, much of this will soon very rapidly become humanly impossible. So we're going to have to build models that multi-dimensional models, right? And so this is an example of a model that has my inputs in this model is still relatively simple: are temperature, concentration, and the ligand type, right? And I can add many more other concentrations to it and generate slices. The output is the number of layers, right? So we can essentially build models that will factor in what is the dependence of the unit cell thickness or the particle thickness on different parameters, right? And this is going to be essential, because as we explore these vast spaces, we're going to have to move beyond one variable at a time methods. We're going to have to so this is a paper we've got recently. It's an invited review that has recently appeared in Dalton Trends, where we sort of think about this. And so you can think about taking a synthesis, right? And instead of just empirically following a procedure you found and changing a few parameters, one variable at a time, and this is something that is taught to you in laboratory science, is you should keep everything constant, change one variable, right? And I'm asking you to throw that out, right? And to move to a whole new paradigm where you change multiple variables at a time, and then build a good model that captures this, right? And so this will allow us to understand what are the features that control a certain synthetic outcome. So is the synthetic outcome affected more by temperature? Is it not affected by the concentration? What is the importance of the specific features? And then from working from there, can you do this idea of inverse problem solution, right? Can you predict synthetic outcomes? Can you even derive a synthetic recipe based on this model that will get you to the target that you're looking to get to, right? And again, all of this is impossible to do just by human experimentation alone, just given the vast amount of space that you need to sample. And so I think we're going to have to very quickly move into this paradigm as a means of sampling these areas. So this is again work of Rachel Davidson and Eric Brand. Okay, so that was the quantum dot. So like I said, the big challenge with the quantum dot, though, right, is that it's great for absorbing light, but then it decomposes when you put it in water. So why does it decompose? Primarily because of photocorrosion, photoanodic corrosion. So one of the things we have to do is to regenerate an electron in a hole. We have to get the hole out very quickly. So this is an idea that we started working on several years ago, about almost 4 or 5 years ago, in collaboration with a group of Dave Watson at University of Buffalo, and my students on the project were Kate Pelcher and Peter Marley, and then Chris Millieville at the University of Buffalo. And the idea is that, okay, so you set a quantum dot, right? And then this hole is really the origin of the photoanotic corrosion. If you could very quickly take the hole away, right, then that would be great. And then you could take the hole and you could, at a dark anode, you could do water oxidation, and at this photocathode, you could do H plus the hydrogen, right? And so our hypothesis is that, if you have certain states that, and this is where the title of the talk comes in, of electronic structure design, if you have certain states that can essentially very rapidly transfer holes and serve as hole as hole acceptors, we can do two things. We can protect the quantum dots from photocorrosion, and we can effectively separate the electrons and holes, right? So the electrons, if you can grab the holes, get them to move fast, then those holes are not going to recombine with these electrons, okay? And so what we wanted, states that are positioned at just the right energy for doing water oxidation, that are not going to squander all this energy like TiO2 does. And so we started by thinking about these lone pairs of electrons, filled 5 s2, 6 s2 states that appear in the p block of the periodic table. And we took as a canvas this structure alpha V2O5. And we basically say, look, why V2O5? Because we've got the ability to do redox here, and we can put in many different sorts of ions inside the interstitial sites of V2O5, and therefore change the positioning of mid-gap states. Okay, and so this is a practical example of this is lead V2O5. So lead sits inside these tunnels, and lead's got these 6s2 states that are just at the right energy, or so we thought, for taking holes out of quantum dots, right? And this is hard X-ray photoemission spectroscopy, where we actually see what these are. So turns out lead 6s hybridizes with oxygen 2p as well as lead 6p, and we get these bonding and anti-bonding configurations. And these aren't really non-bonding states, so they're slightly anti-bonding states. The bonding states are here, the anti-bonding states are here, and they're at the top of the valence band. Okay, so they're positioned right where you want them to be to interact with these quantum dots, right? So we can start putting together a heterostructure. So this is we can do it two different ways. We can take lead V2O5 and we can grow quantum dots on it, and this is an example of SILAR, right? So you can see how quantum dots are now on these wires, or we can even take a little bit more sophisticated approach where we use a bifunctional linker, and we can link up the quantum dot using a molecular linker, so that the thiol moiety is bound to the quantum dot, and the ammonium moiety is bound to the nanowire. Okay, so our first attempt, and it fell a little short. So we did get very, very good overlap of lead 6s states with the valence band edge. But as you can see, that here the valence band edge for CAD selenide is a little bit high, and so we'd really like to push this a little bit higher. And so another way of thinking about this is this system we picked is one where we can make a lot of alterations, and this is really how leaves evolved over hundreds of thousands of years, with little tweaks that allowed them to be more and more efficient. Right, and I think a lot of the literature, if you take one material and you get frozen into it, it can be very hard to tweak all of the energies, the thermodynamics and the kinetics to get this to work. So one tweak that's actually shown here, if you actually move from CAD selenide to CAD sulfide, you do better in terms of overlap. But there is a trade-off. CAD sulfide does not harvest the solar energy spectrum just as effectively, and so. When we made these, this is an example of the sort of the overlap of the CAD selenide and lead V2O5 states. So this is a so it works. We've got substantial overlap, but the energetics are not perfect, right? So with this revised lone pair model, this gives us some sort of a design principle to think about what to do next. So obviously, if you want to try to raise the energy level of this mid-gap state, one of the things you'd like to do is go to tin right here, right, on the periodic table, right? But before we get there, okay, so the thermodynamics are kind of okay. They're not perfect, but thermodynamics is not sufficient. The kinetics also have to work, right? So so if you're going to get the hole out very rapidly, can hole transfer compete with electron hole recombination? So we're exciting the electron, you have a hole. Can we get the hole out faster than the electron comes back, right? So this is a huge challenge. And so what's really shown here in blue are all of the desired processes. You want to promote an electron, have the hole transfer into this mid-gap state of lead B2O5 or another p-block compound. We want to have this transfer to the oxidation catalyst. And on this side, we want to have this quantum dot do electron transfer to a reduction catalyst. And then we're going to have this rate of proton reduction take place faster than any of these recombination cycles shown in red. So really, again, thermodynamics is great, but it doesn't get you all the way there. You also have to have kinetics. So we've looked at this using transient absorption spectroscopy, and as it turns out, we can. I'll skip some of the details, but we can do spectroelectrochemistry, and you can see how the electrons and holes are lined up. And essentially, this is the signature for holes. This is the signature for electrons. Okay, and then when we have quantum dots on here, we can see that the signature for the holes is just greatly exaggerated, and within less than 1 picoseconds within the measurement time scale, we've gotten the holes out of the quantum dots. And then if we measure it on a faster time scale, we can actually see the bleach of the quantum dot recover as electrons get transferred, from the quantum dot to the wires. But we start off with very strong hole signal. So essentially, within less than 1 picosecond, we're able to get the hole out. So this is really good news, because it means that we can, by quickly getting the hole to transfer, we can prevent photocorrosion of quantum dots, and we can use these light absorbers. This for about 2 decades, this had been a challenge. We can finally use these quantum dots in photocatalysis, right? So this is the idea. We'll take the hole, go to the dark anode, and then do reduction here, and this works. This works quite well. This is an example under photoillumination. You can see that the cat solenoid, that B2O5, shows very well resolved photocurrent spikes, and you can do sort of hydrogen generation with very good Faraday efficiency, about 95%, and also very stable over a period of time, right? So the reason for the stability is simply, again, our ability to take the hole out before the quantum dot corrodes. So as I showed you, this is not a perfect system. The energetics aren't absolutely perfect. So in the last few minutes, right, I'll take 5 minutes to think through the system. And so part of this what we like in the flexibility of the system is this. I showed you lead B2O5. Well, the vanadium oxygen connectivity can be dramatically varied, by you can sort of almost like the Japanese art form of kirigami, right? But you can make different shapes out of these pyramids and polyhedra. Number 2, we can control the valence band of light harvester by choosing different quantum dots. That doesn't have to be these. There's a vast majority. And so Dr. Tokir Ahmed's group, for example, and Amir Mehtab's a wonderful graduate student with Dr. Ahmed is doing beautiful work on these graphitic carbon nitride groups. We've got we can tune the positioning of the mid-cap states by picking different p-block elements, and then by picking mixed metals by putting M and M prime, so that we can very subtly tune the energetics of these, and then also the interface between the components, right? And so one of the first things we did, and this is work of mostly of Jun Sang Cho and Justin Andrews, going from lead to tin. Okay, sure enough, just like you would predict, cat selenide is now perfect. Cat telluride even works pretty well now. And so the challenge, though, is how do we make tin V2O5? So this was not a known compound. So Justin Andrews came up with a method using topochemistry. He started with this beta prime copper V2O5 phase. He took the copper out. He has this zeta V2O5 structure. And then reacting it with tin oxalate, he can generate tin V2O5. This is a new compound. And by putting quantum dots on it, right? This is an example. We can do much better water splitting. So this is an example of designing a new compound that fits the needs of thermodynamics and kinetics in the system, right? And so from theory to reality, we can make this happen, right? And this is an example of really good photocatalytic performance. Again, sub-picosecond hole transfer and very good bonding so this tuning example of tuning this mid-cap state that was published a couple of years ago, and so we can really expand this repertoire, and this is our what we've tried to do because there's just so many options here, right? And I just want to show you this. I'm going to elaborate in subsequent talks. This is alpha V2O5, but we can isolate all kinds of metastable polymorphs with different V2O5 connectivities. And this is zeta, this is gamma prime, this is lambda. And then we can fill any of these p block elements inside these to control the positioning of the mid-cap state. And so just to show you an example, this is lead V2O5 beta versus delta. And really the delta phase, gets you a little bit more of a bump in terms of the energy positioning of the mid-cap state. And then this is our synthetic route to delta tin V2O5. Okay, so again, so we've got multiple knobs to tune in the system. One of them is simply which p block element you use, lead, tin, and so on and so forth. And the other is what is the connectivity of the lattice that you use. And by independently controlling that, you can tune the structure there. So this is an example of beta versus delta. Another example, thallium. I wouldn't recommend it. It's a little bit toxic, but just to demonstrate the proof of concept that you can tune the positioning of the mid-cap states again. And very recently, this is work by Joseph Handy and Justin Andrews again. You can tune it by changing the group of changing lead for tin or thallium or bismuth, or another option is to co-intercalate. So this is the beta lead or beta tin structure. Here's some new compounds we've made where we've got copper and lead in different ratios, right, sitting at different sites. And so this very rapidly gives us a whole range of compounds, over 120 new compounds that we already sort of have in the system. And so that you can start thinking about this as really evolving a photocatalyst, right? So you start with different possible frameworks, think about which p block element that you want to put in there, think about how to change the valence band edge of your absorber, and then build out heterostructures and binary interning heterostructures and answer these questions about thermodynamics, right? What sort of band alignments are needed, and what type of interfaces enable rapid and directional charge transfer, right? And I'm going to skip this for today, but we spent a lot of time thinking about how do you remove platinum from the system, because the use of platinum is not going to be sustainable. So how do you devise platinum-free catalysts, and mostly moly sulfide. And just really one story that I want to tell you, work of Abhishek Parija. This is, moly sulfide is known to be a great catalyst for the hydrogen evolution reaction. What Abhishek was able to do using a combination of X-ray microscopy is really figure out what sites in moly disulfide transition metal dichalcogenides are actually catalytic. So this is some work where he was able to show, based on the spectroscopic signatures he was able to detect in X-ray microscopy, we could essentially show that it's these corrugated edge sites that are the origin of catalytic activity. And this is exactly what it looks like. and these are the sites that correlate with having very high, very high catalytic activity that we can measure in an AGR reaction. Okay, and there's another signature for this site in sulfuric acid. So you've got two different spectroscopic probes, and so the idea is, well, you look at a catalyst that works. What are its spectroscopic signatures, and what happens when those spectroscopic signatures disappear? And you nail down what exactly are these sites. Okay, so I'm going to stop here, and really, happy to take any questions. So just to sort of summarize, the mid-cap states from these p-block cations can be precisely positioned to enable hole extraction. That solves this long-standing problem we've had and enables the use of quantum dots to deliver, to harvest the solar spectrum, deliver holes, and we can, this ultra-fast hole extraction gives us this composite that is able to very effectively harvest solar spectrum, do water oxidation, and really specific edge corrugation motifs in molybdenum sulfide have allowed us to design, increasingly more active catalysts for that are earth abundant and sort of precious metal free for hydrogen evolution. And really another thing that I want to sort of leave you with is this is a lost space to be sampled, and I think it's perhaps not going to be humanly possible. So we're going to need some sort of a human machine interface to deal with this. So thank you again for your patience and for listening to me, and I'm happy to take any questions.
Thank you, Professor Sarbajit, for this very informative lecture on designing catalysts and understanding their electronic structures. There are a number of questions because the topic is such a burning topic for most of them, and I guess many of the participants are working in this field where they have a number of queries which I would like to put up to you one by one. So should I start with the questions?
Yes, please. Yeah, I think I can't see the chat window, and I have to
yeah, exactly. So, yeah,
right. Yeah.
So the first question was asked by one of the participants based on how electron mobility effect in electrocatalysis reaction takes place.
Yeah, that's a really good question. So of course, if electron mobility is limited or is constrained, then you're essentially going to have a challenge with catalysis, right? So having excellent electron mobility does not solve all the problems, but so again, it's one of these things where having a reasonable electron mobility is a necessary but perhaps not sufficient condition for electrocatalysis. And I skipped the section where we were talking about we were working with MOS2 and trying to essentially charge dope it, and we've had some success with using NC60 to get some pretty good charge doping in there, and that seems to help increase the electrocatalytic activity. But of course, mobility is one thing, right? But you still need very active sites, and so designing active sites is sort of the other issue that if you're going to work at low over potentials, that's a whole separate issue.
One of the participants wants to know about the 4D model which you explained, and he wanted you to elaborate on the 4D model with some specific examples. Yeah.
Sure. So the point is that this is a really good question to bring up, and to the point of that I was talking about, when we develop syntheses in the lab, right? There is so many questions, so many variables to vary. So temperature, concentration, and perhaps your the rate at which you mix the reactants, the injection rates. There's the ligands you add. There's just so many different variables, and it quickly turns into 5, 6, 7 more dimensional space, right? And a lot of them become really hard to even visualize. So the point is, I think, to use at a minimum something like machine learning to understand what is the sensitivity of your outcome to different variables, right? And then to start to appreciate, I think our human brain has trouble dealing with high dimensional space, and has trouble with visualizing representations in high dimensional space. But trying to understand that really a lot of synthetic work we do is very prone to biases because we are always changing one variable at a time, and that, you know, oftentimes you have you have synthetic design spaces that are not neat at all. So how do you sort of go into this regime of high dimensional spaces and mapping, you know, these spaces to arrive at synthetic outcomes with much greater precision and accuracy than we currently do? Okay, so I think this is going to be very important. So the example I showed you was a relatively simple one. It had, you know, temperature, the type of ligand, which is captured in the form of the diffusion coefficient, and then it had the concentration, right? So it's three-dimensional inputs and one output, but you can quickly get much more complicated just even with this system.
There's another interesting question based on quantum dots. They want to know that how so far quantum dots have proven beneficial in reality in case of water splitting. And the part 2 of the question is, which specific part of the periodic table is more exciting and beneficial for water splitting reaction to make quantum dots?
Yeah, so, you know, well, so commercially quantum dots, the major challenge has been stability, right? So, you know, right now the commercial application of quantum dots is in, you know, television screens and such, where they're very well protected. And the biggest challenge to ultimately has been, you know, is the one we've solved in 2018, very recently, or really in 2019, is the idea of how do you protect them in water. And so these p-block compounds, by doing ultrafast hole transfer, this is how you can make quantum dots viable, right? Or at least viable against photoanodic corrosion. There's other things that also have to play their role. In terms of, you know, what part of the periodic table, I mean, we love our p-block transition metal oxides because we have a combination of the mid-cap state that we can tune, as well as the redox properties we need often to do catalysis. But, you know, light absorption comes across the periodic table, right? Depending on, you know, even in main block elements like carbon nitrides, you can have very tunable absorption, or, you know, you've got your 2 6s and 3 5s that do the indium phosphide. There's a lot of interest in 3 5s because that's a relatively, you know, less toxic combination. So I think lots of different opportunities there. Including you know, earth abundant options that folks are working on.
There are 2 questions based on vanadium pentoxide. One is that what is the difference between all the vanadium pentoxide structures and which is good in terms of photocatalysis?
Right. So the vanadium oxide structure. So vanadium oxide has what is called the rich energy landscape, right? So I showed lots of examples of energy landscapes, and let me see if I can switch back to that. And so it's got a very rugged energy landscape, which means that there's many different forms of vanadium oxide, like you can see here. And this is the landscape I'm talking about. So local minima. So this image doesn't have axes on it. The axis could be anything really: temperature, pressure, you know, ion concentration, chemical activity. Right, and then you can essentially think about these as just like the comparison I mentioned about diamond and graphite and buckyballs and carbon nanotubes that Dr. Sarma also brought up. These are all different polymorphs of V2O5, and there's more than 10 that we can make, and there's at least you know 8 others that we predicted, and so in terms of what works, this is our current best performer, as long as you've got something like tin in it. And this is a system based on theory and some initial DFT work and some initial Haxby's work, where we predict is at least slightly better, perhaps a lot better than Zeta V2O5. It's this structure here, lambda or delta. It's a double layered structure with tin or another p-block cation inserted between the layers.
The other question on vanadium oxide is that can we have other than MXV2O5 structures that could be used for water splitting?
Oh yeah, absolutely. And I didn't expand beyond this, but it's a really good question. We have lots of V3O8 structures and VO5 structures. So again, the what we're generally looking for is a p-block and a transition metal together and that has reasonable band alignment with a quantum dot. This is a vast space, and of course, depending on what sort of quantum dot you pick, where you want to pick the quantum dot that gives you the maximum overlap with the solar spectrum, right? Cadmium telluride is good because it is a commercial photovoltaic material, but there's other ones coming. And so as long as we can match those band gaps, with our different oxides, we can be in business in terms of harvesting holes and capturing the solar spectrum effectively.
There's another question on, can we use the oxygen produced by the electrolysis of water as source of oxygen for COVID patients?
Oh yeah, that's a really good question. I mean, of course, there's purity issues, but it's yeah, absolutely. I mean, I think electrolytic generation of oxygen, doing it safely and at a high enough concentration, if you can deal with these overpotential issues, and you can separate it from hydrogen, that's for sure. One of the ways that people do produce oxygen, right, in large scale electrolyzers.
Then there's another question on how to make electrolysis of water affordable and easy to use for oxygen production. Yeah,
that's a really good question. So large scale electrolyzers have numerous problems. So the Department of Energy has a roadmap, that also sort of specifies how to address these. So some of the problem, not all, lies with the catalyst, right? So we still, I think, are struggling both on the oxygen evolution side as well as the HER side from replacing precious metal. Okay, that's a big part of the cost. But indirectly, a big part of the cost are the large stacks that are required for electrodes, and the large stacks often also come from simply the overpotential being large and the catalyst being suboptimal in their performance. So you can not just address, you cannot just replace these with cheaper catalysts, but we need better catalysts so you can cut down on the entire stack cost. If that makes sense. I think I saw a question about why can't we plant more trees? Well, trees are too slow, right? So if we're going to do this on any sort of reasonable time scale and move towards replacing, let's say, all of the gasoline that is consumed in the world with hydrogen, okay, we're going to have to do photocatalysis on a much faster scale than trees are capable of.
Someone has recently posted what is the production rate of oxygen and hydrogen by photocatalysis as compared to conventional electrolysis. And
yeah, that's a really good question. So solar to hydrogen records for the best direct solar to hydrogen are still low. So I forget what the rate is, but I want to say about 7 to 8% is the efficiency for solar to hydrogen. So that's something that has to come up a lot higher if you're going to do solar hydrogen production. Now, having said that, there's all sorts of, one of the things we've discovered, there's all sorts of reasons why people want to have hydrogen. For instance, on one of the areas where we got a lot of interest from is large scale ships, tankers, right? Which are often extremely polluting. There's some big time regulations coming down from the International Maritime Organization that's going to demand upgradation of fuels. And so one of the things they're seriously looking at is even if the efficiency is not so great, even if the solar to hydrogen production rate is not bad, generating hydrogen in the deep seas could be commercially viable at even relatively low rates of relatively low efficiencies. And this is true across lots of sites that are not connected by pipelines, where you don't have alternatives for fuels. So I think that you're going to see the first sort of production of solar hydrogen take place, and it is already taking place in areas such as mines, which are kind of remotely located, deep seas, areas, drilling sites, offshore drilling sites and such. And then finally, I think it's going to start slowly entering into more mobility or storage, grid level storage applications.
Well, thank you, Professor Sarbajit, for such an informative lecture, and it was really insightful because it had started from the basics of catalysis to the advanced methods that are being adopted to design different oxides and different metal structure frameworks for obtaining efficient water splitting. And I'm sure all the participants are so inquisitive, and they've been actively listening to all the lectures, and they've been posting questions. So I thank you very much for your active participation in spite of sparing some time from your busy schedule and helping us enjoy the lecture and gaining more information on this topic, because this is really a very interesting topic of research which is going on widely even in our university at our department, and there are many students who are willing to work in this field in future as well. So this was very, very informative for all of us. Thank you very much for providing us such an informative lecture on such a hot topic of research.
Thank you very much, Dr. Riaz, and looking forward to the remaining lectures and the lecture that's coming right up from Dr. Ganguly. Thank you.